Hello students, we are going to continue with some more examples and some real-world applications before we summarize our learning about similar figures. In this example, you see a lot of dimensions. Let's talk about what these dimensions mean. Do you see how the 6 runs from here to here? It's talking about this height of the blue triangle. The 30 is from here to here. It's talking about the height of the green triangle. The 40 is talking about the base of the green triangle, and the 8 is talking about the base of the blue triangle. The x corresponds with the hypotenuse of the blue triangle, and the 50 corresponds with the hypotenuse of the green triangle. Taken together, it looks a little overwhelming, but what we can do is separate that big shape into two smaller shapes, like this. Notice I've taken the same dimensions, 6, 8, and x, placed them on the blue triangle, 6, 8, and x. Taken the same dimensions, 30, 40, and 50, and place them on the green triangle. So if you ever feel overwhelmed with the organization of similar figures, you may separate them into two separate entities, two separate looks. Now, our goal is to calculate the missing measurement. And when I look at the missing measurement, I find it on the blue triangle on the hypotenuse. So this is going to have to be part of my ratio. So I'm just going to put x over. And my ratio is going to start with a hypotenuse measurement. Now, what I relate my hypotenuse to is up to me. I have the options of relating it to the height of 6 or the base of 8. I'm going to relate it to the height of 6 because 6 is a smaller measurement. It's going to make my calculations a little bit easier. So I'm relating my hypotenuse to my height. I'm just abbreviating so that I remember. So on the smaller triangle, it'd be x for the hypotenuse, 6 for the height. So x over 6. Now I need to write a similar ratio here. Hypotenuse of 50 to a height of 30. And I want a hypotenuse to height ratio. So the hypotenuse is 50 to the height, which is 30. Since these are similar figures, they have the same angles. We see right angles here, acute angle of the same measurement. I know these are similar, which means that their sides are proportional. X times 30 makes 30x. 50 times 6 makes 300. So 300 is equal to 30x. Divide each side by 30, and we get 10 equals x. So this missing dimension, if this triangle is to be similar to this one, then this missing dimension has to be 10. Now, we do not know if it's 10 inches, 10 feet. We know that it's 10 units. Whatever these units are, the 10 will have as well. Now, let's look at a real-world situation. Suppose that you're on vacation and you want to know the height of this palm tree. Unfortunately, all you have is a tape measure and you're too short to reach the top of the tree. So you're going to have to measure this indirectly. Even though you can't reach the top of the tree, you can measure the tree's shadow. And you see that when the sun is shining on the tree at this point in time, it has a 10-foot shadow. You then measure your shadow and you say, well, I have a 2-foot shadow. And I know that I'm 6 feet tall. So how tall must the tree be? We have a similar situation here. We have similar triangles because the sun is hitting the tree and the person, creating similar triangles between their shadows, their height, and the ray of the sun. Height, shadow, and the ray of the sun. Do you see how we have two similar triangles? We do not know the height of the tree, so that's going to have to be part of my ratio. So I'm going to let height be the top of my ratios. I only have one measurement to relate that to, and that's the shadow. So I'm going to write a height to shadow ratio for each object. X height to 10 feet of shadow, 6 feet of height to 2 feet of shadow. Since the sun is hitting them in similar manners, we know that their ratios are going to be equal in value. X times 2 makes 2x. 6 times 10 makes 60. So 60 is equal to 2x. Divide each side by 2, and we get 30 is equal to x. So the tree is 30 feet tall. And we didn't even have to measure it. That is called indirect measurement. Let's do one more practice problem. If a 5-foot tall student, okay, so they're not giving us a picture, but we can draw it. A 5-foot tall student casts a 35-inch, that's almost 3 feet, 35-inch shadow. How tall is a giraffe that casts a 98-inch shadow? And we want to know, how tall is this giraffe? So we can write two ratios, one for the giraffe and one for the student. For both the giraffe and the student, we can start thinking about the height and the shadow. The giraffe's height is unknown, so we'll use a variable, and the giraffe's shadow is 98 inches. The student's height is 5 feet, and the student's shadow is 35 inches. Now, before we start calculating this, I want to draw your attention to the units. We have this set up correctly because we have the heights on the top, the shadows on the bottom. Notice both shadows are measured in inches. So what do you think both heights are going to be measured in? Good, they're going to be measured in feet, because we want to stay consistent. Feet to inches, feet to inches. Now we can solve. X times 35 makes 35x. 5 times 98, 98 times 5 is 490. So 490 is equal to 35x. Divide each side by 35, and we get x equals 490 divided by 35, which is 14. So that means that this giraffe is 14 feet tall. And we didn't have to measure the giraffe. Indirect measurement. To summarize our learning, similar figures have equal corresponding angles and proportional side lengths. When similar figures are congruent, all of their measurements, angles, and side lengths are equal. When similar figures are enlargements or reductions, their side lengths are proportional. This allows us to use cross products to find a missing amount.